Here's a small puzzle to start with. Suppose you're at a buffet and there's a stack of plates in front of you. Now, what can you actually do with that stack? You can add a plate to the top, you can remove a plate from the top, and that's genuinely it. You can't reach into the middle, and you can't sneak one out from the bottom without the whole thing collapsing. It seems almost too simple to be worth naming. But hold that thought, because this exact rule, only ever touch the top, turns out to be exactly how your computer keeps track of what it's doing. Every time a function calls another function, your computer stacks that call on top of the last one. When that inner function finishes, it gets popped off, and control returns to whatever was underneath. Your browser's back button works the same way, so does undo. So this incredibly restrictive rule, you may only touch the top, isn't a limitation at all. It's actually what makes the behavior predictable. And that tension between restriction and reliability is something we're going to see again and again. Now, let's change one small thing. Instead of a stack of plates, imagine a line of people at a coffee shop. At first glance, this feels like the same idea. People join, people leave. But notice the difference. Here, the first person to join is the first person served, not the most recent one. This is a small change on paper, but it completely flips the character of the system. A stack rewards whoever just arrived. A queue insists on fairness. First come, first served, no exceptions. And once you notice this pattern, you start seeing it everywhere. Your print jobs are a queue. Your messages arrive in a queue. Customer support tickets, quietly, are a queue. So really, what we have are two almost identical structures. Add to one end, remove from another, that differ in exactly one rule, which end you remove from. And that one rule is the entire difference between last in, first out, and first in, first out.
Here's a question worth sitting with for a second. If you wanted to insert a new person into the middle of a long line, what would that actually require? If everyone's standing in fixed numbered spots, like assigned seats, inserting someone means shifting everyone after them down by one. Annoying, but doable. But now imagine something slightly different. Instead of fixed spots, everyone is simply holding the hand of the next person. Nobody knows the whole line. Each person only knows one thing, whose hand they're holding. To insert someone now, you don't move anyone. You just have two people briefly let go, grab the new person's hands instead, and you're done. One tiny local change and the whole line has updated. This is the idea behind a linked list. You give up instant access to the 47th person. You'd have to walk the chain to find them, in exchange for insertions and removals that barely cost anything at all. It's a trade, not a strict improvement. And which trade you want depends entirely on what you're trying to do.
Suppose you're the mail carrier for a large apartment building, and you need to deliver a letter to a specific tenant. The naive approach, check every single mailbox until you find the right name. But of course, that's not how it actually works. Every mailbox has a label, and that label tells you exactly where to go. No searching required. A hash map is built on exactly this idea. It takes a key, say a username, and runs it through a function that instantly tells it which box to look in. The remarkable part isn't just that it's fast, it's that it's equally fast whether there are 10 mailboxes or 10 million. That single property, constant time, regardless of size, is why hash maps show up absolutely everywhere in software, quietly, in the background, doing this same trick over and over. Let's end with a game you've probably played before. I'm thinking of a number between 1 and 100. You guess, and I tell you higher or lower. If you're playing well, you don't guess 1, then 2, then 3. You guess 50. Then, depending on the answer, 25 or 75. Each guess cuts the remaining possibilities exactly in half. A binary search tree takes this game and bakes it directly into how data is stored.
Smaller values live to one side, larger values to the other, all the way down. So searching for something isn't a matter of checking every item. It's a matter of repeatedly asking left or right and watching the problem shrink by half each time. And once you see it this way, something nice happens. These 5 ideas, stacks, queues, linked lists, hash maps, trees, stop feeling like separate, arbitrary rules to memorize. They start looking like different answers to the same underlying question. Given some constraint on how you're allowed to access things, what's the most useful structure you can build? That question, it turns out, is most of what computer science is quietly built on.